Hey, these are the MAT 1140 notes. This is chapter 8.4, inverse and combined variation. Now, I want to point out that the last couple of notes really didn't have a whole lot of explanation. They were primarily examples. I apologize, sometimes that happens in my head. So hopefully I can pull some stuff together for you with these notes. We are going to talk about inverse and combined variation. And the one thing I want to make clear is the difference between direct variation, which is what we did in the last section, and inverse variation. So with a direct variation, okay, we are talking about the relationship between our x and our y, our input and our output. With a direct variation, as x gets bigger, y also gets bigger. Don't know why this is in here twice. Sorry. Believe it or not, I did proofread and apparently missed it. With an inverse variation, again, we're looking at the relationship between x and y, between our input and our output. Here, as x gets bigger, y gets smaller. Now, up top, we have two different objectives. It says solve problems of inverse variation using proportions. I am not going to use proportions to solve these. Proportions, in my mind, make more sense with direct variation. I am going to solve everything using that second objective, the constant of variation. Okay? Now you'll notice when you look down here at the examples, I did pull the examples right out of the book. So if you want to compare how to solve these with an inverse variation, with the proportion, which is what the book does for these two, versus the constant of variation, you can do that. Okay. Here's what we want to remember when we talk about inverse variation. Our constant of variation, that k, we get from multiplying the corresponding x's and y's together. Okay? So for example A, I've got machines and I've got days, and it doesn't really matter what I call x and what I call y. 5 machines, 8 machines, 12 days. How long? How many days, right? So we're going to use this. I'm taking my, it doesn't even matter what I call x and y. X and y, I'm multiplying them together, 5 times 12. That is going to equal, and I'm just going to keep it consistent over here, x and y. That is going to equal 8 times y. Now, does it matter if I call it x or I call it y? No, it doesn't. So we are not worried about that. But we know how to solve this. This is a one-step, divide both sides by 8. And I get y equals, 5 times 12 is 60. 60 divided by 8 is 7.5 days. And you will notice if you look in the book that proportion is set up so you do get to this spot right here. This 5 times 12 equals 8y. For me, it makes more sense to set it up this way than it does with the proportion. Okay. So I've got a 10-inch diameter gear in mesh with a 5-inch diameter gear. 10 inches obviously larger. The larger gear has a speed of 25 revolutions per minute. So I want to know the revolutions per minute for the smaller gear. My 10-inch gear has a speed of 25 revolutions per minute. My smaller gear, again, it doesn't matter if I'm calling it x or y. Divide both sides by 5. 10 times 25, I will write it out here because I left myself a little more room. 250 divided by 5 is 50 equals x. X is 50 revolutions per minute. RPM. See, sometimes my mouth works faster than my hand. So when we are talking about an inverse variation, keep in mind, remember what I said at the beginning, as x gets bigger, y gets smaller. Makes sense that when we multiply them together, we get the same number for any xy combination. Okay. Now we're going to talk about problems that use combined variation. So hopefully that's enough to get you through. Combined variation means that we are going to have some direct variation. Keep in mind with the direct variation, we multiply the constant of variation, and we're going to have some inverse variation. Okay? And that's where we are, let's look at it this way. If xy equals k, right, that is how I use the constant of variation for inverse relationships. If I want to solve for just one or the other, that's my constant of variation divided by the other value, okay? And that's going to come into play here. So in a relationship, P varies directly as M. Let's see if I can color code here. Varies directly as M. P, here's my constant of variation, K, varies directly as M. And inversely as N. Directly is getting multiplied by that constant of variation. Inversely is dividing the constant of variation. So here they tell me my constant of variation is 18. M is 14. N is 28. When we multiply 18 by 14 and divide by 28, we get 9. Okay. Directly as M. Inversely as N. So let's take a look at B here. This would be a good time to pause and see if you can set this one up and then come back and compare. Horizontal beam safety supports a load P that varies jointly as the product of the width W and the square of the depth D. So P varies jointly. Remember, our joint was with a direct. W times D squared. Varies jointly. Right? I'm multiplying. I got the width. And I've got the square of the depth. Inversely as the length L. So the first piece is just to get this set up correctly. Now I am going to figure out what I can fill in. So a beam that has a width of 5, a depth of 12, which has to be squared, and a length of 8 can safely support 1,260 pounds. That's the load, 1,260. So here, we've got to solve for K first. I'm going to multiply both sides by 8. And then I'm going to divide both sides by 5 times 12 squared. So take a minute to make sure that makes sense. Here my 8's cancel, my 5's cancel, my 12 squareds cancel. All I'm left with is k. 8 times 1260. Remember, if you're plugging this into the calculator, if you are dividing by this whole thing, you want to wrap that in parentheses. Or you want to divide by 5 and then divide by 12 squared, or 144. Either's fine. Okay, now we want the safe load in pounds. So now we're actually answering the question. We had to find that constant of variation before we could do this. Safe load, my constant of variation is 14. Here, same dimensions, same material, so width and depth are the same. It's only the length that's changing. As our denominator gets bigger, the amount of load it can hold gets smaller. And there's the inverse variation part.